Hello, welcome to chemistry class, Unit 5, Alcohols and Ethers. We are going to start from alcohols. Today's lesson is Introduction, Classification, Isomerism, Nomenclature and Physical Properties of Alcohols. Introduction. Alcohols are organic compounds that are derivatives of hydrocarbons where one or more hydrogen atoms of a hydrocarbon is or are replaced by the hydroxyl groups. They are represented by the general formula CnH2n plus 1 or H or CnH2n plus 2 O or R or H, where R is a radical, and this radical may be an alkyl group or allyl or phenyl group. Let us have an example. If N is equal to 1, the formula of alcohol will be CH3OH or molecular formula CH4O. But here we have R, which may be a phenyl group. We can have the following alcohol. Classification of alcohols. We can classify alcohols in different ways, but the main classification is based on the type of carbon on which the OH group is attached. Here the main classes of alcohols are primary, secondary, and tertiary alcohols. Let us start from primary alcohols. These have only one alkyl group attached to the carbon carrying the OH group. Here we have an example. The carbon in red is a primary alcohol, and it is the one which is carrying the OH group. And it is a primary alcohol because it is attached to only one other carbon. So the molecule here is a primary alcohol. Second class is secondary alcohols. These have two alkyl groups attached directly to the carbon of the OH group. Example. Can you see the carbon in red is attached to two other carbons, so it is a secondary carbon, and the molecule is a secondary alcohol. The last but not the least is tertiary alcohols. These have three alkyl groups attached directly to the carbon carrying the OH group. An example, you can see the carbon in red is attached to three other carbons, and it is a tertiary carbon, so the molecule is a tertiary alcohol. Let us continue with the exercises. Classify the following alcohols as primary, secondary, or tertiary alcohols. Feel free to pause the video and try the exercises, and after you continue. Other classes of alcohols. Alcohols in which the OH group is attached directly to an aromatic ring are called phenols. Here we have examples: 4-methylphenol, 4-bromo, 3-methylphenol, and phenol. Alcohols can be classified as monohydric when they carry one OH in the chain, or polyhydric or polyols when they carry more than one OH in the chain. Here we have examples. The examples in the left side, they are polyols because one has 2 OH in the group, another has 3 OH in the group. And the alcohols in the right side, they are showing monohydric alcohols because each one contains only one OH group in the chain. Nomenclature of alcohols. According to IUPAC system, alcohols are named by replacing the final E of the parent hydrocarbon with OL, then specify the position of OH group before ending by OL. Examples: CH3OH, which is an alcohol deriving from an alkane CH4. Its name is methane. So if we want to name this alcohol, we replace the ending E of methane by OL, and the name of alcohol becomes methanol. The second example is CH3CH2OH, which derived from the hydrocarbon called ethane, And if we want to name this alcohol, we can replace the ending E of ethane by OL, and the name of alcohol becomes ethanol. The common names of alcohols. Common names are constructed by adding the word alcohol to the name of alkyl group. Examples: CH3OH, and here the alkyl group is called methyl. And if we want to construct the name, we are going to take the name of alkyl group and we add alcohol, and here the name will be methyl alcohol. Second example, CH3CH2OH, the name of alkyl group is ethyl, and if you want to construct the common name of this alcohol, we'll say that it is ethyl alcohol. Other examples of naming alcohols using IUPAC rules. The first example is CH3CHOH CH2CH3. The first step is choosing the parent chain, and the parent chain is the longest ending carbon chain, which has many OH groups and many branches. In our case, the parent chain is CH3CH2CH3. Second step is numbering the chain in order to give the location number to the substituent. We can number from the left to the right or from the right to the left. From the left to the right, we have 1, 2, 3, 4, and the position of OH is 2, but from the right to the left, it is 3. So, the appropriate direction is from the left to the right for this example. After numbering the chain, you are going to assemble the name. We start by writing the stem, and the stem is the prefix indicating the number of carbon in the parent chain. Here, because we have 4 carbon, so the stem is built to mean 4 carbons. After the stem, we add the stem suffix, which is indicating the type of bond between carbon atoms in the parent chain. If they are only single bonds, we use AN. And then we add the position of the OH group, which is 2, and remember to put hyphen between the number and the letter. After we put the ending, and the ending, because it is alcohol, it is OL. So the name is butan-2-ol or 2-butanol. Second example, we have CH3CH2CH2CH2OH. We choose the parent chain. After choosing the parent chain, we are going to number the chain from the right to the left, and then we assemble the name, which will be built AN1-ol or butan-1-ol. The third example, we are going to choose the parent chain, and here is the parent chain, and we have the branches CH3CH3 and the OH substituent, and we number the chain from the left to the right, which gives position 4, but from the right to the left, which gives position 2, so we choose from the right to the left, and the position of OH is 2. If we have OH and the alkyl groups, the priority is given to OH because this is the one which is taken as a functional group. The rest are as substituents. Now we assemble the name and we form 4,4-dimethyl pentan-2-ol. The fourth example, we choose the parent chain, and here we have a 2 OH group. If we want to assemble the name, we are going to add the prefix di to show that there are 2 OH which precede OL. So the name, it is going to be ethane 1,2-diol. But here you see we keep E of ethane. This is to make this name readable. In order to avoid two consonants to be consecutive, we put a vowel between them. It means that if we had no positions between, we could read ethane diol. But if there is no E, it will not be easy to read. The common name of ethane 1,2-diol is ethylene glycol. The fifth example, we choose the parent chain and we have 3 OH groups. So we are going to assemble the name by using the prefix tri to show there are 3 OH in the name. So the name is going to be propane 1,2,3-triol. And the common name of this molecule is glycerin or glycerol. Number 6, we choose the parent chain. After choosing the parent chain, we have 3 substituents which are different: chloro, methyl, and OH. If we have other substituents like chloro or methyl and we have OH takes priority over them, and when numbering the chain, we give the lowest position to OH and others follow. So we number the chain from the right to the left. So when we assemble the name, it will be 4-chloro, 4-methyl, pentan 2-ol. We start with the chloro because chloro comes before methyl in alphabetic order. The example number 7, it is a cyclic alcohol. When we have a cyclic alcohol, the carbon having OH takes number 1 when numbering. So we number the chain like this one, and then the name of the alcohol is cyclohexane 1-ol or cyclohexanol. You can see here we use the word cyclo in order to show that the chain is cyclic. If you don't put cyclo, someone will write an open chain. Number 8, it is a phenol. A phenol, this is an alcohol in which OH is attached directly to the benzene ring. And here, the name of this one, which is very common, is phenol, but the systematic name, it is benzene 1-ol or benzenol. Number 9, we choose the parent chain, and here we have a double bond in the chain. So when numbering the chain and you have a double bond, which one do we give priority? Is it double bond or OH? OH takes priority over double bond and the triple bond. So numbering the chain, we start from the right to the left in order to give OH the lowest position possible. And here, the triple bond will be on the third carbon. So the name of this will be pent 3N1-ol or pent 3N-ol. You can see the stem suffix has changed, where we had used AN and here we are going to use EN because there is a double bond. Number 10, it is an aromatic molecule but which is not a phenol. Why it's not a phenol? It is because OH is not attached directly to the benzene ring. There is CH2 between OH and the benzene ring. That's why this is going to be named differently from number 8. How do we name? We choose the parent chain, which is CH2, and the benzene is going to be taken as a substituent. So that's why we are going to name it as 1,2, and it is attached on the second carbon because OH was given priority. And the name will be 2-phenyl-ethane 1-ol or 2-phenylethanol. Activity. Name the following molecules. Feel free to pause the video and try these molecules by naming them using IUPAC rules. Isomerism in alcohols. Monohydric alcohols mainly exhibit the following three types of isomerism: chain isomerism, position isomerism, and functional group isomerism. Let us start with the chain isomerism. The chain isomerism is the existence of isomers which have the same molecular formula but different carbon connectivity, meaning that different skeletal structure. Here we have an example, C4H10O, which has two isomers, beta-1-ol and 2-methyl-propan-1-ol. If you look at their structures, you can see beta-1-ol, the carbon connectivity is a straight chain, while 2-methyl-propan-1-ol, the carbon connectivity is a branched chain. Three carbons connected together and another one is attached as a branch. So these are chain isomers. Position isomerism is the existence of isomers which have the same carbon connectivity but different positions of the functional group. Here we have example C3H8O, which has two isomers, propan-1-ol and propan-2-ol. Looking at their structures, you can see they have the same connectivity, they are all straight chains, and the only difference will be in the position of OH group, which is a functional group, where in the first example it is 1 and the second example the position is 2. Functional group isomerism, existence of isomers having the same molecular formula but different functional groups. Here we have examples. The first example, it is showing the functional group OH, which is for alcohols, and the second example, it is showing the functional group O connected to two carbons through single covalent bonds, which is an ether, but the two have the same molecular formula, which means that they are isomers which have different functional groups. Physical properties of alcohols. No alcohol is a gas at room temperature. The lower members are generally liquids up to C5, while the higher ones are solids. This is explained by the strong intermolecular forces between alcohol's molecules, which are the hydrogen bond intermolecular forces. The higher members are solid because as the carbon chain increases, the random dispersion forces increases, and the molecules become very close to each other and they form solid state. Alcohols have characteristic sweet alcoholic smell that can be appreciated or not. This will depend on individuals. Alcohols have relatively higher boiling points compared with hydrocarbons of approximately the same molecular mass. In hydrocarbons, we have only random dispersion forces, which are the weakest intermolecular forces. But in alcohols, we have random dispersion forces, dipole-dipole interaction, and the hydrogen bond intermolecular forces, which are many and very stronger than the random dispersion forces in hydrocarbons. In other words, hydrocarbons cannot form hydrogen bonds. Alcohols form azeotropic mixture with water. If you remember it well, ethanol cannot be separated by water using simple distillation. Why? Because ethanol and water form azeotropic mixture. What is azeotropic mixture? It is a mixture of two or more liquids whose proportions cannot be altered or changed by simple distillation. This happens because when an azeotrope is boiled, the vapor has the same proportions of constituents as the unboiled mixture. The lower members are readily soluble in water, but solubility decreases with the molecular mass. Alcohols are soluble in water because they can form hydrogen bond among themselves, and they can also break the hydrogen bonds formed by water and form new ones with water. But when the carbon chain increases, the non-polar part of alcohol overweighs the polar part of alcohols and reduces the solubility of that alcohol. You remember, likes dissolve likes. If the non-polar part increases and the water is a polar, the solubility will be decreasing. That's why lower molecules are very soluble, but longer chain molecules are less soluble. Alcohols are less volatile than alkyl halides of similar mass. This is because alkyl halides don't form hydrogen bond intermolecular forces among their molecules. Polyols or polyhydric alcohols are more viscous than monohydric alcohols of the same number of carbon atoms. This is because polyhydric alcohols have many sites of hydrogen bond, while monohydric alcohols have few sites of hydrogen bond. Further explanations on physical properties of alcohols. As you can see, methanol molecules can form hydrogen bond between themselves, which explains why methanol is not gaseous at room temperature. Instead, it is a liquid because of strong intermolecular forces, which are hydrogen bond. Another diagram is showing that water can form hydrogen bond with ethanol, or ethanol can form hydrogen bond with water, so they can hydrogen bond each other. That's why ethanol is very soluble in water. Thank you for your kind attention.